Cette conférence va maintenant être enregistrée.
Thank you, Cédric. So I will be moderating this webinar with my colleague Cédric Delporte. And first, I would like to remind you some good practice for the webinar. Please remember to turn off your microphone and your camera. Also, please don't hesitate to ask questions in the chat at any time. And Cédric and I will be moderating those questions. And then you can enjoy the talk. Please be aware also that all the webinars that we are organizing with the RFMF can be found back on our website. You can see an example here for the webinar of 2024. So there is 4 webinars per year, and all the if the speaker agrees, all the webinars are registered and put on YouTube and on our RFMF website. With that, I just would like to announce some upcoming events within the RFMF community. We have just launched the registration for our junior autumnal school that will be held between the 17th and the 20th of November in Bordeaux. So please don't hesitate to look at the program, the exciting program on our website as well. And the next webinar will be on the thematic on Fluxomique and isotopy, and will be held on the 9th of October with a keynote speaker that will be Jean-Charles Portet, and will talk to us about Fluxomics, how the metabolism is in action. With that, I will leave the mic to Cédric to introduce our keynote speaker of today's webinar.
Thank you, Marine. So I'm very pleased to welcome and to introduce Tomas Pluskal, who agreed to join us today, even if he's currently in holidays. So very thank you again, Tomas. So I will briefly introduce you, and then I will leave the floor for you, the time that you share your presentation. So Tomas is, of course, in Metabolomics with a background in molecular biology, in biochemistry and computer sciences. He got his master in computer science in 2004 from Charles University in Czech Republic. Then he moved to Japan, if I'm not wrong, where he did his PhD at the University of Hiroshima in 2014. Then he did several postdocs in Denmark, USA, and he finally came back to Czech Republic in 2020, where he's now leading a group at IOCB, so the Institute of Organic Chemistry and Biochemistry in Prague, where he leads the team and the group on biochemistry of plant specialized metabolites. And he's also a co-founder of the MZIO. So today, Tomas is going to present his talk, which is entitled Decoding the Chemical Language of Plants. And I don't know if you could share your presentation.
Thank you, Cédric, for the nice introduction. I'm going to try the sharing. Okay, so you should be able to see my slides now.
Yeah.
Wonderful. Okay.
Okay.
So thank you for Thank you once again for the introduction. That was all correct. So I titled my talk Decoding the Chemical Language of Plants, and I like to start with the story about the plants and plant metabolomics that we do before I go to the more technical aspects of the AI and machine learning stuff. Okay. So why do we find plants interesting? So plants are sessile organisms. They cannot move. Once they grow somewhere, they're stuck to that location, and therefore they rely entirely on chemistry for their defense and adaptation. And over 400 million years of evolution, plants have developed amazing biosynthetic pathways that produce very unique and structurally diverse molecules that somehow give them evolutionary or selective advantage in their particular environment. But oftentimes these molecules can be also useful for us humans, as medicines, for example. And here I highlighted just 2 examples, artemisinin, which is the first-line antimalarial drug, and the artemisinin therapy market is worth over $500 million per year. And also a Nobel Prize was actually awarded for the discovery of artemisinin, as probably most of you have heard. And another example is paclitaxel, which is a chemotherapy drug, and the market of paclitaxel is worth over $1 billion per year. So these are also very valuable molecules. However, plants are extremely diverse. There's over 400,000 known species. If you look in the databases, you can find probably over 1 million of already known metabolites, but this is still just a tip of the iceberg that people have actually isolated and characterized, and there's many more that remains to be discovered. But oftentimes in this natural product research, we have the problem of rediscovery. So we spend time isolating certain molecule from certain species, and then we realize we isolated something that was already reported 20 years ago by someone else. So here comes the workflow that we're trying to now implement in my lab, how to prioritize plant species for sampling. And we are basically going after plants that have not been studied much in terms of natural products. This was developed by 2 postdocs in my lab, Theo and Tito, and is based on a phylogeny of flowering plants that was published in this Nature article last year. And so we start with the phylogeny, and then we annotate the phylogenetic tree with data on each genus that is coming from Wikidata and also from publication databases like Scopus. And we measure how many natural products were reported in the genus and how many papers were mentioned the genus in their studies. And then we can annotate the tree with this data. And so in practice, it looks like this, where we have the phylogenetic tree. And here's an example of a well-characterized lineage where we have some species that have lots of natural products characterized from them and lots of publications about them. Seems like somebody's interfering with the microphone. Okay, and then we have an example of understudied lineages where we have very little that has been published about these plants. And then also with the green mark, you can see species that are available for sampling for us based on the collections of botanical gardens that we collaborate with. So this is the way how we try to prioritize species that we study. And we're collaborating with on this with the founders of the Digital Botanical Garden Initiative, DBGI, which are these 2 guys from Switzerland. So this is a platform, basically an open science initiative to explore and establish robust and scalable workflows for the digitization of chemo and biodiversity from botanical collections to the global scale in wild ecosystems. So we're starting with botanical gardens, and they designed workflows and methods, how to collect all the metadata about plants and how to unify, standardize a mass spec sampling protocol so that the data is comparable across labs. And the goal here is pretty ambitious, basically to collect mass spec data on all the plants in all the botanical gardens. This is how it works in practical experiments. We collect plant samples from botanical gardens. We collect all the metadata that the botanical garden has about those plants. We also provide our own metadata, such as the pictures that we take on the plants and the geolocation data. And we do mass spec analysis, and the LCMS data is also connected to this metadata. And we use a technique that's called knowledge graphs to organize all this data. If someone is not familiar with knowledge graphs, this is an example of a knowledge graph where we have plant species. And then, for example, by LCMS analysis on the plant species, using the MZMine platform, we found some feature. So we have some mass and some retention time. And based on the annotation done by Sirius, we know that this feature is an alkaloid. So we can organize all this data, these results, into knowledge graphs. And you might be wondering, like, why am I talking about this? But I see that this way of organizing data into systematic and organized kind of digital form is going to be extremely valuable to create large-scale data set that can be used then for machine learning and AI applications. As part of this DBGI workflow is also a connection to the iNaturalist website. So this is our lab's iNaturalist profile, where we collect all the observations, pictures from the plants that we collected and analyzed. And you can see the geolocation data, you can see the photos, and this is all again connected through the knowledge graphs. We organize our samples in a very neat and organized way, as you see, and everything is labeled. And so far we have collected about 100 species in a kind of like a trial experiment, but we are aiming to collect all the species that we can find in the Prague Botanical Garden, which is about 20,000, which would then bring us to the largest available metabolomics dataset on plants. This is our sample preparation workflow. This is pretty standard, nothing too surprising. We collect the plant samples, we lyophilize them, we use an electric mill to grind them into powder, and then we extract them with a mixture of methanol and acetonitrile and concentrate the sample and analyze by LCMS. Okay. Now, most of you probably are familiar with LCMS. So from LCMS, you get a data set that looks like this. In fact, what this contains is just millions and millions of some numbers. So it's not so trivial to interpret this. And for interpreting this data, we use the MZMine platform, which I believe some of you may have heard about. This is a project that has been around for a while. So this is a software platform for mass spectrometry data processing and visualization. And MZMine was actually started in 2004, so it has more than 20 years of history behind this. It was started by Matej Oresic's group in Finland. And I joined the project in 2006 after the first release of MZMine. And gradually I took over the project because I needed a good platform to process my own metabolomics data when I was doing my PhD in Japan. So I basically brought the project to MZMine 2, and then afterwards, the community around the MZMine has actually expanded quite a bit. Many people joined the development. And as you can see over the recent years, the number of lines of code has actually been increasing quite rapidly. So the development has taken up pace and lots of new technologies were introduced. So this has sort of culminated in 2023 with the release of this Nature Biotechnology paper about MZMine 3. And there was an effort that was led jointly by Robin, Stefan, and Ansgar here, who were the co-first authors on this paper. And in the following year, we published, together with Tito here, we published an article in Nature Protocols, which describes all the workflows in MZMine, how you can process LCMS data, GCMS data, or mass spec imaging data with or without ion mobility separation. So everything is kind of organized in one large, very comprehensive protocol article. Last year, we actually started a company called MZIO that was already mentioned, that is now continuing the development of MZMine and also providing an enterprise version of MZMine for commercial customers. MZMine stays freely available to the academic community, but we realized that as the project got bigger, basically there is no other way how to maintain it than using some commercial entity, because it just gets too big to be maintained by academic volunteers. And so we started a company, and it has now taken off. So MZMine development has now again taken much higher pace than before. We try to stay connected to the academic community, so we organize these annual MZMine meetings at IOCB Prague. So one just happened a few months ago in April. You can see a photo from that meeting here. And this is not just in Prague. We actually organize various MZMine workshops all around the world. So just from last year, you can see pictures from Okinawa and Seoul and Montevideo in Uruguay. And we also try to be present at conferences such as ASMS or Metabolomics. The Metabolomic conference just took place 2 weeks ago in Prague. So here is a photo from the MZMine workshop at this conference. As you can see, it was very, very packed. Okay, so enough about MZMine. Now I would like to start talking about what's next. So MZMine is now been taken over by a company, and its development is going on pretty much fine. So what is now my lab focusing on? And here I have to say that if you ask someone in 2005, 20 years ago, what is the biggest bottleneck in metabolomics? They would probably say it was metabolite annotation. If you ask metabolomics people now, what is the biggest bottleneck in metabolomics, they're going to say the same, into metabolite annotation, particularly if you're working with complex samples like plants. How is this possible? Like, what is the reason that this is so difficult and it has remained a bottleneck for 20 years? I think it's because we have very little reference data. So typically people rely on spectral libraries to annotate their peaks or their features in their mass spec data. But the amount of data that we have in the spectral libraries, either commercial or freely available, is just low. Here you can see a comparison of known natural products and known human metabolites. And this is the molecules that you can find in spectral libraries. So it's only very little portion of the molecules that we already know, and we have some reference data for them. And these spectral libraries are also used as training data for various tools, such as Sirius that annotates spectra. So the fact that the spectral libraries are too small is also affecting the performance of these tools. So what can we do about it? One thing that we can do is certainly build bigger and better spectral libraries. And the second thing that I think we can do is we can use the unannotated mass spec data and do some machine learning magic using that data. So in my lab, we are trying to do both. So first, I'm going to talk about building spectral libraries. And here we try to build really large-scale spectral libraries, and not only on MS2 spectra, but also MS3, MS4, up to MS5. So we do multi-stage collisions. So when what I mean is we are building this MSN spectral tree. So here's an example of one spectral tree from this molecule, this tripeptide. We collect the MS1 spectrum, the full scan, where we isolate the precursor. And then we do MS2, so we find all the peaks in the MS2, and we isolate the most intense peak or the fragments in the MS2 spectrum. We repeat this process in MS3, and again, we isolate the most intense peaks and go to MS4, and again, up to MS5. And we do this in a positive and negative mode, and we also try to vary the collision energies. So that means for each compound, we collect about 100 different spectra. And experimentally, we use a robotic pipetting system that can pipette libraries of molecules into 1,500 well plates. So each well contains 10 different molecules in a mixture. And then we use a flow injection setup in the mass spec where we don't have any LC column, but we just use one pump that delivers the sample, and then another pump that delivers the solvent for the LC. And this is all going directly into the mass spec. So we can see the signal of the molecules for about 90 seconds. And that gives us enough time to collect all the spectral trees for all the 10 compounds that we see in that mixture. So then for the different precursors, we build these spectral trees. And this is followed by a data processing workflow, which we implemented, of course, in MZMine, where we extract all the spectra from the raw data. We build the spectral trees for each precursor. We annotate the spectral trees based on the description of the spectra of the compound database that we are analyzing, so we know what each precursor belongs to. And we do some quality checks to remove chimeric spectra or like poor quality spectra. And then we export all the libraries into standard formats like JSON and MGF. So this was initially a project done by Corina, a postdoc in my lab, and she analyzed these 6-7 libraries of compounds, altogether about 32,000 unique structures. And like I said, for each structure, we collect about 100 spectra, so it's actually a lot of spectra that was collected. And this is not just done by us, but we're trying to put together a worldwide initiative that we call Merlin, Mass Spectral Library Network, where essentially anyone who has a mass spec can join in and can help us to collect data on molecules, and all this data will be uploaded into a common repository. So it's all open and it's all accessible to everyone. If you're interested in this topic, you can take a look at the paper that's under this QR code. And in the paper, we have about 30,000 molecule data that's already uploaded online. But we are at the moment already at 60,000. We analyzed 30,000 more, and we have about 200,000 more compounds incoming. So our goal is to collect all these spectral trees on 300,000 standards by next year. And since Corina has already moved to her next job, she's running a core facility in Vienna, my new postdoc Federico is taking over this project and continuing this. So if anybody has access to compound libraries, please let me know. We would be very happy to include them in our analysis. And now the second topic is how can we use unannotated MS data? So even if we acquire standards data on 300,000 compounds, it's still a very small number compared to the whole diversity of chemicals that you can find in nature. But there is a lot of data in repositories such as Massive that is not annotated. It's a real data on real spectra analyzed from real molecules, but we don't know what they are. So for this, we can borrow an approach for machine learning that has been very successful in text processing or natural language processing. And it's, for example, in ChatGPT, you have something that understands written text very well. And the way that these large language models are trained is they use a huge database of text. And you take the text and you hide some words. So if you hide some word, you can ask the model to predict what is the missing word. In order to do that, the model has to first understand something about the meaning of each word, how the words are connected, how they relate to each other, what is the context of the text, what is the emotion of the text, and so on. And so you can train the model again and again on billions of pieces of text until it gets pretty good at this task, which means it's sort of understood the language. And so we borrowed this approach and we use the same approach on mass spectra. So we start with a huge amount of unannotated spectra, and we hide some peaks in the spectrum, and we're asking our model to predict what are the missing peaks. In order to do that, the model has to understand something about the structure of the data, what it means to be a spectrum, about the relationships between these peaks, about the relationships between the different molecules that are hiding behind the spectra. But we can do it again and again for millions and millions of spectra. So for this, we first had to assemble high-quality data set. If we just take raw Massive, it contains billions of spectra, but many of those spectra are actually coming from proteomics data, or they're coming from low-resolution instruments, or they are not of very high quality. So we actually did an extensive filtering where we checked what is the resolution and the mass accuracy of the spectra in each file. And we collected only the highest quality spectra that we know are coming from metabolites and have charge 1 and so on. And with this, we got a data set that we call GEMS. And then this is about 24 million high quality and unique spectra. And so each spectrum is different. This is what we start with. And we developed a pipeline for this model that we call DREAMS, which stands for Deep Representations Empowering the Annotation of Mass Spectra. It's a little bit complicated. As you can see here, there are various modules that you can see in other machine learning architectures like transformers. One thing that we realized is that machine learning or neural networks are generally not very good at dealing with precise numbers. But if you're working with mass spectra, you actually really care about the precision. If you have 0.001 Dalton difference, that's already a significant difference. So we had to introduce an additional layer here that's called the Fourier features, which is a kind of technique that allows the neural networks to process precise numbers by replacing them with some sort of collection of sine waves. I don't really understand the technical details myself, but basically this is what allowed us to keep the precision in the calculations. And then we trained this on this task that was to predict the missing peaks in the spectra. And by doing this again and again on a large database of spectra, we got a model that sort of understands what it means to be a spectrum. What is interesting is that this model also understood something about molecular structures, despite never seeing molecular structures. Everything it has seen was just mass spectra. And how we noticed that was, as we keep training this model, this red line, that is the training loss. So this is basically just saying that the model is getting better at reconstructing those hidden peaks. So this is normal. But at the same time, as the model is getting better, it is also getting better at predicting molecular structures. So we can, at each point, we can freeze the model and retrain it on just a small number of chemical structures to see how well it performs in predicting chemical structures. And as the model is getting better at reconstructing peaks, it is actually getting also better at predicting chemical structures. So this is quite interesting because the model was not trained for that purpose. So now what we can do with this model is that we can convert each mass spectrum into a numerical vector. It's called an embedding, and that basically represents an internal representation of this spectrum in the space of all possible mass spectra that are understood by the DREAMs. And then we can visualize these DREAMs embeddings as a space. So in this case, this is a UMAP projection. And you can see that it sort of starts making sense. Like there are carbohydrate molecules in green, there are halogenated molecules in pink, and it all naturally starts to be organized into some layers, even though the model itself was only trained on spectra. Now this has turned out to be quite a powerful method for looking at mass spectral similarity. If the two spectra are very close in the DREAM space, so we say they have a high DREAM similarity, this tells us something about the similarity of the molecules that are behind that those spectra, even though the spectra, if you look at them visually, they look quite different. And if you just calculate a traditional cosine similarity, you would probably be close to 0. Whereas these two other spectra, they are far away from each other, so their DREAM similarity is low. Now, if we look at the molecules that these spectra actually represent, you can see that these molecules, I mean, they are different, but they have these like indole moiety and the phenyl moiety here and 3 nitrogen. So there is some clear kind of visual similarity between these chemical structures. And so it makes sense that the DREAM's embedding actually comes very close. But if you calculate the cosine similarity, as I mentioned, you would not get those spectra very close. Whereas in contrast, these two molecules are completely different. So we actually show in Roman's paper that DREAMs can be used as a state-of-the-art spectrosimilarity method for comparing spectra based on molecular similarity. So here we have the similarity of the molecular fingerprints, and we compare that DREAMs actually performs better here than MS2 Deep Score on representing this molecular similarity with the spectral similarity. It's also a state-of-the-art method for library retriever or for analog search from molecular libraries or using molecular networking. And recently we also implemented this DREAMs spectral similarity in MZMine. So you can use directly from MZMine, you can create molecular networks. You can create molecular networks using the DREAMs similarity. It connects your spectra. And you can visualize the results in the standard visualizers in MZMine. Here is one example that we found interesting. Here we have a molecular network from a data set and that connected these two nodes. And these two nodes actually were annotated. And now we know that they belong to these two structures. And you can see that the cosine similarity of this spectra is actually very low. Even the modified cosine similarity is 0.19. So these two spectra would never be connected in a traditional molecular networking setup. But if you look at the molecules, they sort of all have similar structural elements. So it actually makes sense like they are kind of penicillin-based antibiotic-like molecules. So it actually makes sense that we connected them together, but it would not be possible using traditional cosine similarity. Another thing that we have done is we collected data from massive on 200 million mass spectra of small molecules, and we put them together into a huge network that we call the DREAMS Atlas that's built using the DREAMS similarity of the spectra. And this is something you can call the Internet of mass spectrometry. Right? So all these molecules have some relationships against each other. And then this DREAMS Atlas can be used to connect data across the different data sets and to build new hypotheses. So for example, here we have some spectra that are coming from very different data sets that, according to the DREAMS similarity, form a cluster that has very high similarity. So most likely, these all correspond to either the same molecule or very similar structurally related molecules. And we have samples from human hand and human face. We have samples from some fruits and trees. And we also have a standard sample of a fungal pesticide here. And we have a sample from a human disease, the psoriasis disease. And this is interesting because the cause of the psoriasis is unknown, it's unclear. And by this, we could form a hypothesis that maybe this disease could be somehow linked to the use of this pesticide, which obviously we can then find on the human samples and also on the fruits and in other pesticide mixes. So this could be used to form a new hypothesis. Another example like this is where we have a large network of molecules that are highly similar and coming from various data sets, but we can see that we have different types of cancer here. We have a lung cancer, we have a renal cancer, we have a brain glioma. So potentially there could be some molecule that could be effectively used as a cancer biomarker, even though we don't know at this point what the molecule is. And another example from plants. So here we have a molecule that's coming from various plant species, again in very different data sets, but even though we don't know what it is, it's only coming from plants. So this is definitely a plant-specific molecule that's abundant in many different species across the phylogeny of plants. Now, what you can do is you can also calculate an average of these embeddings for each spectrum across a whole data set. So if your data set contains 5,000 spectra, you can use DREAMS to calculate the embedding of each spectrum. And simply by averaging all these embeddings, you get an embedding for that sample, for the data set. And then you can use same UMAP visualization tools to organize your data sets. And as you see here, it starts making sense. So here we have food samples, and all the data sets from beverages are kind of clustered in one cluster. All data sets based on plant-based food are organized in one cluster, and animal-based foods are organized in another cluster. So this is a very powerful way how you can organize your data in a very computationally effective manner. But DREAMS is not only about spectral similarity. So when we start with the mass spectra, we can use the DREAMS to calculate the embeddings in the embedding space. And then we can use these embeddings to make various predictions. And I'll just show some examples here. For example, we can predict the presence or the absence of fluorine in the molecule that is hidden behind the spectrum. And this is a very difficult task in mass spectrometry. Another thing we show in the paper is you can predict molecular properties such as drug likeness, or we are currently working on developing a novelty detection algorithm. So we can predict how novel that molecule is without actually knowing the molecular structure. So here's the example about detecting fluorinated molecules. Fluorinated molecules are potentially very interesting because they are very common in drugs and agrochemicals. So somehow empirically, it is very useful to put fluorine into molecules if you want to make something that's commercially useful or successful. But it is very difficult to detect fluorinated molecules because they have only one natural isotope. And because my lab is working in plants, we're also studying some plant species that can make fluorinated molecules. And so far, there's only 2 known fluorinated metabolites, that is fluoroacetate and fluoroleic acid. And with the fluoroleic acid, even the data is a bit shaky, so we're not really sure if it actually exists in plants or not. So we would be very interested in detecting more fluorinated molecules from plants. And this is my PhD student, Andrei, working on this project. And he collected a number of plant species that are known to produce fluoroacetate. We ran them on the mass spec, and then we used the DREAMS model for a fluorine prediction. And we selected the very high confidence hit. So the spectra where our model was very sure that they contain fluorine. We isolated those 10 molecules that our model has predicted, and actually using NMR analysis, we confirmed that 9 of them really contain fluorine. So we found 9 new fluorinated metabolites from plants, which is very exciting since so far only 2 have been reported. So if you're interested in this DREAMS model, feel free to take a look at this paper under this QR code. This is a work of my PhD student, Roman. And now where are we going with this? Obviously, we have the DREAMS Atlas, that's very powerful, but we still don't know what the molecules are. But we are working on a method how to convert the DREAMS embeddings into actual molecular structures. And as you can imagine, this is a very difficult task, so we might not be able to always reconstruct the full structure of the molecule, but it's still very useful if we can predict some version of the structure and then give some confidence rating that, for example, this part of the molecule we are very confident about, and this part of the molecule we are less confident about. So this is something similar that AlphaFold does with protein structures, because it gives you some confidence level for some parts of the structure, and then some parts may be less confident because AlphaFold is not so sure. So we're trying to develop something similar for molecular structures predicted from mass spectra. And now if we actually develop a method to predict molecular structures, the question is, how do we know that we are actually doing better than other tools, like Sirius, for example? And so we developed a benchmark for this. And this is an idea that was actually a group effort started at this Computational Metabolomics and Dutch tool seminar last year. So you can see Roman is here, and he initiated this effort. It was a really great team effort where we designed a computational benchmark that includes a data set of spectra and 3 tasks to either annotate the spectra using de novo generation, so with no prior knowledge, just generate a structure de novo, or with molecular retrieval from chemical structure database. So you give it a database and the algorithm has to rank which is the top structure for this spectrum from the database, or in the reverse problem, a simulation of spectra. So given a molecular structure to simulate the mass spectrum for this structure. So this is called a mass spec GIM, and it includes a data set, and this is coming partly from the data set that I mentioned that was collected by Corina in my lab, but also from some public data from GNPS and MONA, where we only selected a high resolution, high quality spectra. So this is currently the largest high quality spectral data set covering about 30,000 molecules, but of course we're planning to further expand it with the new data as we collect them. And most importantly, we included very carefully designed data splits. So some part of the data you can use for training your method, and then another part of the data you can use for evaluating the performance. So this is called data splitting. And it is very important to avoid any kind of data leakage from the training data to the testing data. So the molecules, if there are very similar molecules in the training data and in the testing data, then actually the method can just remember something from the training data, and therefore your performance would be inflated higher than the real performance of the method. So we took care of this and designed some baseline methods that one can compare against. And as you can see, the baseline results for the de novo molecular generation, which is the most difficult task, the accuracy of all the baseline methods is actually 0. So this shows how difficult this task is. And any kind of method that actually goes above 0 is already a great improvement. This includes a website on the Papers with Code platform where you can easily plug your code, you can test your new method, and it includes this leaderboard. So currently the diff-MS model that's designed by Connor Coley's group is the state of the art, is performing the best in the mass spec gym benchmark with the accuracy of about 2.3%. So we still have a long way to go. And mass spec gym was published at the NeurIPS conference last year. Here's again a link to the paper, and it actually generated a lot of attention. Here's a photo from the poster session at NeurIPS where our whole team was very busy explaining the concepts and the data sets behind mass spec gym. So we hope that the more people from the machine learning community are going to join in and develop new methods using this benchmark. So with this, I would like to thank my amazing lab and thank you all for attention, and I would be happy to answer questions.
Many thanks, Thomas, for this very complete and interesting presentation of the different tools that you are developing in your team. So there is applause in the audience, and there is already a question. So the first question is from Johan Perrier, who is asking, thank you for the very clear presentation. I was wondering whether you have considered integrating synthetic data, in parentheses, synthetic mixture of or single metabolite data, to address the lack of data, especially annotated data. For instance, by generating in silico MSMS spectra from chemical structure.
I think this is definitely one thing that we're thinking about for the future, because in machine learning, generating synthetic data set has proven many times to be a very powerful way how to advance the methods. But it has to be done carefully, and it has to be done at the point where you can be confident that the synthetically generated data is actually high quality. And this is something that I'm not quite convinced yet that the currently available method for generating synthetic spectra are good enough to bring like significant benefit here. But like I said, we now have the benchmarks, we now have the tool, so we can definitely explore this and evaluate how well it can advance these problems.
Great, thank you very much. I do have a question about the difference in, so Johan Perrier is saying thanks to your answer. It's about the similarity calcul that there is in DreamMS. How is it different from the one from GNPS exactly? I might have not exactly the difference in the similarity calcul.
So GNPS is using a cosine similarity. So that's essentially looking at the spectrum and calculating some similarity metric from the common peaks that you have. And based on what I was showing, you could see that we have sometimes spectra that actually look different, and they don't have any common peaks.
Yeah.
But according to the DREAMS similarity, their similarity is very high. So if you do this in GNPS, the spectra would not be connected because the cosine similarity would be very low. But according to the DREAMS model, the similarity is very high. Now, we can only speculate why this happens, but I showed some examples of the chemical structures that we have data for, and that actually shows that, yeah, the DREAMS model might have some like good point there, that there are actually chemical structures that result in very different spectra. If you look at the structures, you can clearly see some structural elements that they have in common. So it makes sense to connect them.
Right. Okay, thank you.
Actually very hard to evaluate objectively because we don't have really ground truth data on spectral similarity.
Yeah, definitely. And I do have another question. It's rather about the database building that you are doing. So if I understood properly, you are injecting mixtures of 10 metabolites at a time. And I was wondering how do you choose those 10 metabolites? Do you have any solubility, co-solubility problem? Or what are the parameters to choose which metabolite you are going to mix together?
I mean, there's basically only one requirement, that they have to have different masses. And because we don't want to have chimeric spectra from the two different molecules with the same mass and then mixing up together. So we select molecules that have different masses so we can isolate them in the mass spec. We don't care so much about solubility and about other things because we are going for throughput. The more compounds, the better. So we need tens of thousands of compounds. And of course, some of them we will not detect. So some portions of them we just don't see and we don't care. We just go for more compounds.
Okay. It's like a high throughput. So there is two other questions. Niek is asking, could you give some more details about how you were able to clean the annotated data for training dreams? And do you think there is a risk of introducing some bias in the data by that cleaning process?
Okay, the cleaning process was actually quite extensive and it's described in detail in the paper. So I don't think I can go through it in detail right now because it would probably take a long time. I would suggest to take a look in the paper where it's described. But introducing some bias, I mean, in a sense, yes, because we only focus on high resolution spectra, preferably coming from Orbitrap instruments, but not only from Orbitrap instruments. So there is definitely going to be some bias. I mean, the biggest bias is that we only included positive mode ionization spectra. So that's a huge bias, right? The model doesn't work at all for negative mode spectra. Well, that can be fixed in the future. I mean, we can train another model for negative mode spectra. Other types of biases, possibly. I mean, one thing is, what I also observe in other domains of machine learning is that if you train something big, it takes a while for the whole community to really understand like what's inside, how it works, how it performs in different tasks, where are the strengths, where are the weaknesses. Because it just takes time. And then this is, I think, the stage where we are at now with dreams. So we're trying to understand now ourselves, where are the strengths and where are the weaknesses, where are the potential biases, what we need to improve.
But it's very promising. And Mehdi is asking, have you seen some cases where DREAM-S can be wrong on its spectral similarity measurements?
Yeah, I mean, this is, again, a bit tricky to define what is wrong, right? If we have some examples of molecules that are clearly different, but dreams somehow decided to connect those spectra together, then the answer is no. I cannot think of such example, but doesn't mean it doesn't happen, right? This has to be evaluated in a way that would be somehow objective, and that's tricky. We are working on this together with Ming Wang from the GNPS team, trying to currently design some benchmarks where you could get some objective idea on how spectral similarity metrics actually perform. But like I said, it's a tricky question.
And one last question, will we be able to use your similarity score directly in R, for example?
So the dreams, everything is implemented in Python. I think it should be pretty easy to use it in other languages or platforms using some Python wrappers. This is essentially also what we do in MZMine, because MZMine is implemented in Java, but it is using the dreams model and it works. I assume in R there must be some way how to load these models and then use them from the R environment, but I don't have any experience with it myself.
Okay, great. Thank you very much, Tomas, again. A lot of people are thanking you in the chat, and it was really a great presentation. And we will thank you again for taking time on your holidays and leave you back to your family.
Thank you very much.
Thank you again so much.
Enjoy the rest of the webinar.
Thank you very much. Great. So we're now gonna go to our next speaker, and we're gonna welcome Madina Bekbergenova. Sorry if I misspell your family name. So Madina is doing a joint PhD in chemistry between the University of Côte d'Azur and the computer science at the University of Antwerp in Belgium. She's under the supervision of Louis Félix Notias and Ruth Betrumer, and her research focuses on computational method for mass spectrometry metabolomics data, and she will present her work right now.
Okay, thank you very much for your warm introduction. Can you hear me well?
We can hear you well, but your presentation is not in full screen yet.
Okay, yes. Yeah, now you should see it in the full screen.
Yes, we do. Thank you very much.
Okay, well, good afternoon, everyone. I'm Madina, and I'm happy to be here today to discuss the project that we've been working on. It's called Métabolomique, and it's a multi-agent AI system which accelerates data mining in mass spectrometry-based metabolomics. So, as all of us know, mass spectrometry metabolomics generates a large amount of data, which is usually stored in different databases, and then we need to go through those databases and download the experimental data for further analysis. But one of the emerging and exciting ways of representing your experimental data is through the use of the knowledge graphs, which has been just mentioned by Tomas. So here we are referring to the experimental natural products knowledge graph that incorporates mass spectrometry data from 1,600 different plant extracts, and is what, as it was previously mentioned, knowledge graph is a graph with different nodes, which can represent either the plant or lab extract or mass spectrometry features, and it has some links. The nodes have some links between, more importantly, you can link the data with some theoretical data and get the holistic view of your experimental data, which is very nice. But then to retrieve the data from the knowledge graph, for example, to get the answer for the following question, which asks about how many signals can be annotated by both Sirius and ISDB, you would have to generate the following Sparkle query, where Sparkle is a semantic web language that is used for querying the knowledge graphs. And then you can run this Sparkle query. Let me take a laser. You can run the Sparkle query on the knowledge graph endpoint and get an answer in a couple of seconds, which is very nice. But to generate this kind of Sparkle queries, you need to be familiar with the ontology of the knowledge graph. So you need to know what kind of nodes and links are present there. But you also need to be familiar with the syntax of Sparkle, which might be a little bit difficult for the domain experts. And it's also time consuming to generate this kind of Sparkle queries. Therefore, the question that arises here is that, can we use large language models in order to translate user question into the Sparkle queries? Because we know that LLMs are capable in different coding tasks, and we have seen good performance of large language models on the translation task. So can we actually use those models for this? So that we can run these Sparkle queries on the knowledge graph endpoint and get our answers in a very short time. And in order to answer for this question, I would like to briefly explain the main components of Sparkle. So suppose we want to generate the Sparkle query for the following question, which asks about the metabolites that are annotated with the ISDB methods in Lavoie trichiloides plant. So basically, we can divide this question into two parts. We're searching for ISDB structure annotations for the Lavoie trichiloides plant. And now, if we look at the schema or ontology of the knowledge graph, this is just a small part of it that we included here, we would be able to find this ISDB annotation node, which basically represents those annotations that we are searching for, meaning that we can use this node directly. But then what about the plant? As I said, the knowledge graph that we are referring here is the experimental natural products knowledge graph, and it has the data from 1,600 plant extracts. Therefore, we cannot have separate plants representing different nodes. But what we do have there is that there is a node called raw material, which basically represents different plants submitted to the knowledge graph. But then how do we make sure that this raw material represents exactly this plant? And for this, if we look at the Sparkle query generated for this question, we would be able to find that the raw material actually linked to some Wikidata identifier, which basically corresponds to the Wikidata ID of this plant. Consequently, we need to have the Wikidata ID of the plant in order to link the raw material node exactly to this plant, which means that we need to provide this identifier explicitly so that we could generate the final Sparkle query using those identifiers. And coming back to my previous question regarding the usage of large language models to translate the natural language question into the Sparkle queries, if we can do it or not, as you have seen, we need to get those identifiers in order to generate the Sparkle query. And we cannot rely on LLM's knowledge alone to provide the right identifiers. Therefore, we need to have some kind of a system, or we need to have a specific tools which would provide those entities so that we could finally construct the correct Sparkle query. So here we are proposing the multi-agent system called Metabolomics. And I will talk about agents in more details in the next slides, but the idea is that the user provides a question in natural language, and then the multi-agent system where as every agent, you can think of a specific worker, which has its own list of tasks to perform, and also list of tools, where tools are basically Python functions, which are explicitly provided. And then depending on the question, the right agent is chosen to choose the right tool. And then the system generates the Sparkle query. It runs the Sparkle query on the knowledge graph endpoint. And here it's important to note that as a knowledge graph, you can consider your own knowledge graph containing your experimental mass spectrometry data, and then the system retrieves the data from the knowledge graph and provides you final answer. So now let's see actually what kind of agents we have. And how does the system work? And every agent actually uses large language model as a reasoning engine to identify which tool to use. So what kind of agents do we have? And what happens when the user provides a question? So firstly, the question goes directly to the entry agent, which analyzes the question and sees if it's a new question or if it's something related to the previous question. And if it's a new question, it would call the question validator agent. And the task of this agent is to ensure that this question could be answered by querying the knowledge graph, so if it's a relevant question or not. And if the question is valid, it would delegate the question to the supervisor agent, which analyzes the question and sees if the question mentions either a chemical class name or a plant name or a bacteria name. So those entities which are needed to be resolved in order to construct the final Sparkle query. And if this is the case, for example, the question mentions a plant name, as it was in the previous example that I showed you, the supervisor would call the KG agent, which has access to its tools. And if, for example, the question mentions a plant name, the KG agent would call the taxon tool, which would run the Sparkle query on the Wikidata endpoint and retrieve the Wikidata ID of that plant and send this identifier back to the supervisor. So now we have the question, we have the resolved entities. We are basically ready to generate the Sparkle query. Therefore, the supervisor would call the Sparkle agent. It would provide the question together with the resolved entities provided by the KG agent, and Sparkle agent would use its tools in order to generate the Sparkle query. It would run it on the knowledge graph endpoint and retrieve the answer back to the supervisor. But it's also possible that the user might want to see some kind of visualization of their final answer. And for this case, the supervisor would call the interpreter agent, which has also its own tools that it would use in order to provide either a bar chart or some kind of a diagram. And then it would send those interpreted results back to the supervisor, and supervisor would finalize the whole workflow and send the final answer back to the user. And Metabolomics is available as a web-based application, so you can try it by following this link. And but you need to provide the contributor key, and we are providing it for you for the duration of today's webinar, so that you can try it. The key is RFMF 2025. You need to put it here, so set a contributor key. But I also recorded a quick demo. So here I am selecting the simple question, which asks about the features that can be annotated by both series and ISDB by comparing the 2D structure of the annotations. And we can see that the supervisor agent is calling the Sparkle query runner agent, which generates the Sparkle query on the backend. Yeah, so here we can see the generated Sparkle query, and it already ran it on the knowledge graph endpoint and retrieved the final answer saying that there are 33,255 features annotated by both Sirius and ISDB. So as you can see, Metabolomics has a quite complex workflow, and in order to ensure that everything works properly, we have done some evaluation. For this, we generated 50 random questions together with reference Sparkle queries, and the questions span different nodes and edges present in the knowledge graph. And we compared 3 different configurations. So based on the current evaluation results, we can see that Metabolomics with all the agents using GPT-4o as a LLM model, we got the highest accuracy. Therefore, the current implementation of Metabolomics uses this language model. And finally, as I said, Metabolomics is available as a web-based application. You can try it. The code is released publicly on the following GitHub repo, and we also have manuscript preprint available. And Metabolomics serves as a proof of concept for the upcoming Metabolomique AI project, which is a multidisciplinary project with more AI agents to come. And finally, I want to thank all our collaborators and my supervisors for their support. And I want to thank you for your attention. And if you have any questions, please feel free to ask.
Thank you, Madina. Thank you very much for this clear and concise presentation of your work. So yes, the floor is open for question. For the moment, I don't see any question yet. Oh, yes, there is a first question. So the question is from Liz. Are you training any agents to help users in interpreting their spectra? For example, can your agents respond to questions such as how many carbons are in the parent molecule of this MSMS spectrum?
Well, with the current implementation, we do not have these functionalities yet, but in the long-term perspectives, as I said, there is an upcoming Metabolomique AI project, and yeah, I guess it would be kind of considered there, but for now, we don't have these functionalities.
But it's in the pipeline, if I understood well, this kind of functionalities.
Let me. For now, the goal of the system is to take the question and then to provide the right identifiers to finally construct the Sparkle query, and then to retrieve the information from the already available knowledge graph. But then the creation of the knowledge graph, it's up to users.
Okay.
If this is the answer for your question, or I might have misunderstood the question.
So I think it's okay, but maybe Liz will just leave a message if she wants some clarification. Yes, I was wondering, meantime, as you say, one of the first things is about the taxonomy, and I was wondering how far you can, I mean, if there is no taxonomy or not Wikidata, or there is a misleading, how can you use yourself or when you get the query, just make sure that there is not wrong identifications? I mean,
what do you mean? You mean like if the Wikidata ID is not provided, how do we ensure if in the final Sparkle query everything is fine, right?
Yeah.
Yeah. So basically for this, the best way to check it quickly is to run the Sparkle query on the knowledge graph endpoint, and then to see if there are no results or if there is some kind of error. And this is the quick checks that are done within the system, especially it happens in the Sparkle agent. And then if it sees that, for example, there are no answers, it's quite possible that either the Sparkle query is wrong, meaning that the identifiers is not correct, but also this information is not available on the knowledge graph. Therefore, we have the second chain coming to rerun the question again and see if there would be new identifiers provided and if the next Sparkle query is going to be better and improved. But this is done only one time, and then if there are still no results, it would be up to user to further work with the Sparkle query.
And so I was wondering how far you can get, I mean, totally aberrant answer, you know, from at the final answer or at the moment. When you test it, do you have sometimes or often very aberrant answer that are provided, or?
Yes, sometimes we do have some errors. So we have different types of errors most of the time because of LLMs hallucinate. We know that they do hallucinate, but we try to minimize it. But anyway, those errors come when the right agent is not called. When, for example, the KG agent responsible for providing the identifiers has not been called, of course, we would not have these identifiers. And in this case, the second chain should go and the question should go again, and so that we hope that the right agent would be called, but we're trying to minimize it.
Okay. Thank you. I don't see any more question in the chat. Yes, I have a question from Jan. Do you know labs that try to install your tool?
Do you know what? Sorry, can you please repeat the question?
Laboratories, some labs that try to install your tool. So some other, I mean, groups that try to install your tools. I suppose from
you mean like if there are some kind of collaborations with Metabolomics and other labs? So far, people can try their own question, but one of the limitations is that it's applicable on the experimental natural products knowledge graph. So far, but so people who want to get some answers from the experimental natural products knowledge graph can use it, but I don't know exactly which labs are using it or trying to run it.
I think Jan would be happy to try it. Thank you. If there is no more question right now, we will go to the next speaker. Thanks again, Madina. Maybe if you have any question for Madina, you can post on the chat and Madina will be pleased, I think, to answer your question. So we will go now. Thank you again, Madina. We will go now with Thibault Etienne. So Thibault, I think he will switch on the camera. Thibault is R&D group leader at Gencovery. So he joined Gencovery in 2022, where he leads the group on innovation in systemic biology thanks to AI. And he developed both data-driven and hybrid mechanistic models to explore gene regulation and metabolic pathways. And so I think then, Thibault, you can share your screen.
I have some trouble.
Okay.
I don't know why.
Don't worry. I think maybe.
Okay.
Is it okay?
Normally, I find the solution. I will.
Okay, I think we lost Thibault, but maybe he's going to try to just relaunch the meeting to be able to share.
In the meantime, just
Yes.
so to keep it up with what is happening in the chat, Niek answered Jan's question to Madina, and he said that he tried the tool and it was already about a year ago, but it is an easy web page to use without installation needed. Thank you, Niek, for answering the question of Jan.
Okay, thank you for this feedback too. So I think that Thibault is going to relaunch. Maybe we can wait still a bit. Otherwise, maybe Niek, if you are ready, I don't know if we switch presentation, if you don't mind.
Would be fine for me.
Yes, Marine, you agree also? We will maybe switch. It will be easier.
Yeah, definitely. And I've put Niek as a presentator. So Niek, you can share your screen already.
Thank you.
Okay, and so, but I will switch and present you maybe Niek. So Niek de Jong is from the Netherlands. So he's PhD student in the Computational Metabolomics group at Wageningen University. Sorry for my pronunciation, even if I'm Belgian. Sometimes Dutch is not that easy. So you are under the supervision of Dick de Reader and Justine van der Hooft. And you are developing software and machine learning models to support the interpretation of mass spectrometry data, particularly for spectra lacking full annotation. So Niek, the floor is yours, and we will just, in the meantime, see if it's all okay for Thibault. So Thibault, just we switch to Niek to make sure that we can continue the webinar. So Niek, the floor is yours.
Okay. Thanks a lot for the nice introduction. So the tool that I'm going to present today is MS2 Deep Score, and it is actually very similar in goal to Dreams, which Thomas already introduced. So you can kind of keep that in mind when you try to understand what I'm explaining. So the tool I'm presenting, it's a new version of MS2 Deep Score, and it enables cross-ionization mode spectral similarity prediction. And what that means and why that would be relevant for you, I will explain in more detail. So first, to kind of set the scene, what I mean with spectral similarity scores are any score between two mass spectra. For instance, the cosine score, I think many of you know, and the idea is that score is high when two spectra are very similar, and that can help you to identify two spectra that, for instance, belong to the same molecule. And there are many variants of these scores. Also, for instance, modified cosine score that is also high if there is a small chemical modification. And for instance, Dreams, a machine learning model, can also make this kind of spectral similarity predictions. And the use cases for these spectral similarity scores are quite wide. So the most common one, I think, is library searching, where you take a spectrum that you measured, that you don't know what it is, you compare it to a large library of annotated mass spectra, and then if the spectral similarity score is high, you say, oh, this is likely the same compound. Or very similar analog searching, where you expand the scope of what you search for, and you also search for closely related metabolites. Or molecular networking, where you create a visual overview of your sample, where spectra are connected and visualized as nodes, and then connected by edges if they are have a high predicted spectral similarity. And it can be very useful for exploring your data set, getting an overview of your data, prioritizing certain clusters of spectra, or maybe even doing some annotation propagation between the nodes. But all these methods that I just showed work at one ionization mode at the same time. But in reality, many people that I know and speak to, they analyze their sample in both ionization modes, so in positive and negative ionization modes. And the reason that people do that is that some metabolites ionize or fragment better in one ionization mode compared to the other. And by analyzing them in both modes, you get a more complete picture of the chemical space in your sample, which can help you answer more biological questions. The weird thing is, though, is that even though it's one sample, the fact that you analyze it in two different modalities means that the current analysis pipelines are often also completely separated. So if you would make a molecular network, for instance, with modified cosine score, then you would have something like this. You would get one network for positive ionization mode spectra, one network for negative ionization mode spectra, but this is not really what you want. It's very weird that you have metabolites in the same sample and then you analyze them separately simply because they were recorded in a different way. What would be better is if you can somehow combine the results of different ion modes into one overview and one analysis pipeline in one go. So you would get one molecular network where you can also see relationship between spectra and metabolites that are chemically related to each other, even if they are only recorded in the different ionization. But currently, this is not really possible. And it makes a lot of sense. Why? Because if you record a mass spectrum in a different ionization mode, then the fragmentation pattern that you record can be very different. So 2 examples from a urine case study I'm showing here, and even if the metabolite is exactly the same, there can be very distinct mass spectra across ionization modes, and scores like the cosine score or the modified cosine score are not able to capture that these belong to chemically very similar molecules. The score is also not designed to do this, but that means that you cannot really use those spectral similarity scores across ionization modes. And the story of today, as you might guess, is going to solve that. So the model I've been working on is MS2 Deep Score, and it's a new version of an already existing model. And the concept is quite similar to dreams. And the idea is that we train a model by showing it many pairs of mass spectra, and we train it to predict chemical similarity. And by showing it many examples of these mass spectra, the model will learn statistical patterns in the data, in the peaks that occur, and use that to actually directly predict chemical similarity. And for this new version of MS2 Deep Score, we made many changes that make it faster, easier to use, and also more accurate. However, there is one thing that I want to talk about today that is really a novel way of thinking about these kind of predictions, and that is enabling the cross-ionization modes. And this is really, you take one positive ionization mode spectrum, one negative ionization mode spectrum, and you directly predict chemical similarity between them. And the cool thing is, this works really well. So to go back to the 2 examples that I just showed you of spectra that can look quite distinct, MS2 Deep Score is actually able to predict high chemical similarity between them, even though they are recorded in different ionization modes. And I think that is very exciting. So to highlight how that can be relevant for you, we did a case study on urine data. And this urine data was collected in positive ionization mode, in negative ionization mode. And by using MS2 Deep Score to create the edges for a molecular network, we were able to create one molecular network that had both the positive ionization mode spectra and the negative ionization mode spectra in one overview. So in orange, pinkish, you can see the negative ionization mode spectra. In blue, the positive ionization mode spectra. And there are some clusters that just have negative ionization mode spectra, positive ionization mode spectra, but there are also multiple clusters that have cross ionization mode links between them. And I think an interesting one is the one on the left here. These are all metabolites that are related to caffeine metabolism, and I think you would expect that in urine. And you can see that about half of them were ionized in positive ionization mode, half in negative ionization mode. And purely on the mass spectrum information, we were able to correctly connect them by using MS2 Deep Score and showing to you as a user that there is chemical relationship between the 2. And I think that is really exciting and will really make the analysis pipeline of those cross-ionization modes samples more informative. So I'm now showing a molecular network, but there are also other ways to visualize this. Tomas already showed with dreams that they had this UMAP representation, and this has a few benefits over molecular networking. One is that with molecular networking, you have to play a little bit with the settings. If you set the setting of when to create an edge too low, you get those big hairballs. I think some of you might have experienced that. And these are very hard to interpret. And the second thing is there is no global distance between clusters that are not connected by each other. So you don't know if these 2 are closely related. and making a UMAP representation, which you can do for dreams or MS2 deep score. You get an overview again of your sample. And here it's a very similar principle. Two nodes that are closely together represent spectra that are predicted to be chemically similar. So here we visualize both positive and negative ionization mode again. And what you can see is that there are quite some that positive and negative ionization mode spectra that also cluster closely together. And by overlaying the predicted structures, you get a very nice overview of your sample of both positive and negative ionization mode in one go. So I think that can be very helpful. So I hope some of you are thinking, hey, that is interesting. I would like to give that a try for my spectra. And if you want to, it's really easy to install. So it's available as a Python package. It's pip installable, and we did a lot of work in making it as easy as we can to install. There are clear tutorials for making molecular networks and making this UMAP plot that I showed. However, we've realized that many of you don't have Python experience, and then it can still be a bit challenging. So to accommodate for that, we integrated MS2 Deep Score into MZMine, just like Dreams has been integrated in MZMine. And that means you can just, by clicking in the graphical user interface, get to molecular networks by MS2 Deep Scores across ionization modes. And I think that is really easy if you have no programming experience. So the work is out as a preprint, and we are processing the revisions right now, so it should be out soon as a paper as well. And in the preprint, we did a lot more analysis of actual benchmarking, showing the correlation between true chemical similarity and prediction. So you can check that out for more details. And since we are having here a webinar about the use of AI in metabolomics, I want to give some general ideas on how you should use that, because I think there is a lot of hype about AI, both in the news when it comes to ChatGPT and that kind of work, but also on conferences where we're all showing those machine learning models. And I think it's very exciting. That's why I'm working on it. But I also think you should not overestimate how capable these models are yet. So there are still mistakes in these predictions. And what I think for these machine learning models is extra difficult, that the uncertainty is often a bit hard to estimate. You just get a score which is high, and then it's often correct, but it's also sometimes wrong. So how I recommend you to use all these new exciting machine learning tools is really as a great way for exploring and prioritization. So if you have 10,000s of mass spectra, you don't want to have to go through all of them by hand to figure out what you're looking at. And there, I think these methods can be super helpful to help you be guided to the mass spectra that are relevant for your research question. And I think these machine learning models are amazing for that. But after that, once you have found interesting examples, it can be very helpful. You should still do validation in the lab by ordering standards or isolating them and analyzing by NMR, for instance. But I think this combination can really streamline that process, and therefore these machine learning models remain very exciting and will keep improving in the coming years to come. So with that, I want to thank everyone involved. So Justin and Florian supervised me and gave a lot of input on this project. Robin is from MZMine, and he helped me with the integration into MZMine and teaching me some Java in the project, which was in the process, which was really fun. And Elena did all the case studies and annotating by hand the mass spectra of the urine case study, which was very helpful. With that, I want to thank you for your attention, and I'm very open for any questions.
Thank you very much, Niek, for this nice talk. There is applause again in the audience. There is no question yet, but I have maybe there is a first question, so priority to the audience. Hi, Niek, great talk. I have 3 questions. Does your tool collapse similar feature ionized in different ion bond into the same node, or an edge will connect them? How about the annotation of the resulting cross-ionized molecular network? Is it something included in the workflow, or does it rely on external tools?
Yeah, great questions. So the answer to the first one, no. Two spectra in different ionization modes are represented as two nodes and then connected by an edge. So we don't really distinguish between high chemical similarity or exact matching. So that is still something the user has to do. So you can look at the mass difference and the certainty. It might be something to look into in the future, but currently it is two nodes connected by an edge. Yeah, and the second question, the annotations, they were done by a different tool. So in the molecular network that I showed, the annotations were actually done manually by Elena by comparing to in-house standards. However, in the UMAP plot, we used an external tool, MS2Query, that I developed for analog searching to give putative annotations. Having said that, MS2Deep is a chemical similarity prediction tool, so it can be used for library searching and therefore can be built, can be used to do annotation, but that's not really the focus in the paper. And I'm going to be working on building a tool to do improved analog searching where you can even search across in different annotated libraries where you can maybe search in the positive ionization library with negative ionization mode spectra. But that's something that we still have to explore how well that's going to work and if this really adds something. Yeah.
Marine, your microphone is off. I don't know if...
Oh, sorry. Yes, I was actually talking, but so yeah, I was asking the question of Antonio. In order to increase connection between nodes in the POS and NEG network, can you use POS and NEG precursor ions?
We already do this. So that was one of the improvements that really improves accuracy, is including the mass of the precursor in the and feed that to the network to improve the prediction. And this works and improves prediction quite a bit. And this works across ionization modes, but also within ionization modes. So yeah, that's a great suggestion. Thanks.
Great. And Mehdi is answering to your answers. Thank you for your answers. Perhaps using an approach such ion identity MN can help to collapse all adducts from different ionization modes.
Yeah, that's an amazing suggestion. I think that would, from a practical standpoint, be really useful to collapse that. And I think we should work together on that to integrate MS2Deep directly with that, so that goes very easy and it's easy to do. So I think that's great future work, but we haven't really worked on integrating that well at the moment. But I think we should do that, definitely. Thanks.
Great. Thank you very much, Nick. There is no more questions. So in order to keep the time on, we will thank you again for accepting our invitation. And we will now welcome Thibault, Etienne. So you should be able to share your screen now, Thibault. So as Cedric mentioned before, Thibault is a research group leader at GenCovery. He joined GenCovery in 2022, where he leads the groups on innovation in systemic biology thanks to artificial intelligence. And he will talk to us today about developing both data-driven and hybrid mechanistic models to explore gene regulation and metabolic pathway. So Thibault, the floor is yours.
Okay, thank you. Do you see my screen?
Yes, we can see it and in full screen mode, so it's all good.
Okay, so perfect. So hello everyone. So thank you for the invitation. And today I will be presenting an approach to robust quantify metabolite using penalized regression, especially applied for time series NMR data. So in this project is a collaborative project between three entities: GenCovery, my company, GreenCell, CDMO, and Biochemistry Research Institute. So before starting, I'm going to do a very short presentation about my company and the product of my company. So at Decoding, our mission is to consolidate and transfer biological and industrial data into actionable insights. We operate across R&D pipeline from the real world data to the production environment. So at Decoding, we are powered by a team with 20 years of experience in bioproduction, software development, and data science. So about the product, we built a platform named Constelab, and inside this platform, you can manage your R&D project. So manage a file, but also run pipeline for analysis and share the results with the community or the member of the project. So this presentation is a part of a broader context with a collaborative project involving 3 partners. So Green Cell, a CDMO with a strong expertise in bioproduction, Biochemistry, a research institute with a strong expertise in the quantification of metabolites, for example, NMR data, but there are also other expertise. And Jong to build some kind of model, hybrid model, to help the biologist, for example, to optimize growth condition or to predict or monitor bioprocess. So in this project, the goal is build digital twin, and for that we need data. And in this project, we use NMR data, and especially 2 kinds of data: pseudodynamic NMR data and dynamical NMR data. So I will explain the difference. So pseudodynamic data generation, pseudodynamic data, NMR data. So we have a bioreactor, for example, a R&D bioreactor of 2 liters, and from it we extract some sample, for example, 8 samples in our project between different timeline. And these samples are freeze, sent to bioreactor, and bioreactor analyzes them using NMR. So this kind of data are completely analyzed, and the most important things is during the analysis, we add a standard to obtain absolute concentration. It's very important, especially for our digital twin, to be strongly interpretable. So on this slide, we can see, for example, on the right, some example of data. So we can follow many metabolites, and for example, the glucose, the lactate, etc. The other type of data is still NMR data, but we call that dynamic data. So to explain a little bit, maybe I'm going to use the pointer. Okay. So here we have a bioreactor. The bioreactor is connected directly to the inside MR flow unit, and this unit automatically sends sample to the NMR to produce data, so to produce spectrum. We extract also bioprocess data. The idea is we generate largely more data than a pseudodynamic process, but these data are strongly complex, and to manage it, we can't manage it manually. So this is an example, but in dynamical data, we run many experiments with different pH condition. Is an important point because we do some variation along time about the pH, and it generates some overlap or complex pattern. And for each experiment, we generate more than 50 time points. So we can imagine we have many spectrum to manage. And if you manage manually, for example, for the 8 sample in pseudodynamic, it takes 1 day. So we can imagine for 300 spectrum. So what is the issue? So dynamical data are not expressed in absolute concentration. So we need to deal with. The volume of dynamical data is too large to process manually. commercial software is not flexible enough to accurately handle and precisely handle the data, for example, due to the variation condition. So how we can accelerate and automatize data processing using already processes pseudo-dynamic data. So the idea of the solution is combine expert knowledge on the small data set, pseudo-dynamic data, and using a machine learning approach to deal with the amount and the problem. All this solution is implemented in Constelab in modular form. I will see the next. So for example, this is a screenshot of Constelab platform. Here is a screenshot of the pipelines to analyze the data. So you have two parts. One part for the pre-processing of dynamical and pseudo-dynamic data. And the second part is to use the pre-trained model to predict the concentration for dynamical data in an automatic manner. So I go deeper in the analysis. So we have first we have some issue about pre-processing. The problem of the data, especially when the pH vary, is we need a good alignment between the spectrum along the time. So the solution we build is a local alignment. So the idea, to just give you the idea, is divide spectrum into a small segment and using cross-correlation, do the alignment step by step using interpolation to align the data, align the signal. Why we did that? Because it's very important to align the data for the pseudo-dynamic data, but also for the dynamical data and between them, especially for the machine learning model. So this is an example, for example, of the results. So I take just one example, the acetate example, so acetate peak. So here on the left, we have unaligned data, and on the right, aligned data. We can see the algorithm works clearly well, and especially for the dynamical data. Because during the dynamical process, we do some variation of pH, so there are some trouble about it. The second part of the pre-processing is the binning. Of course, is very important, and especially the binning must be the same between pseudo-dynamic and dynamical data to the machine learning model. So once again, we built a flexible algorithm based on some heuristic and some mathematical formula. So the idea is to detect a peak. We use some algorithm, and for each peak detected, we use how can I say that, an heuristic to calculate the area under the peak. Why is it important? Because we want to related concentration estimate by an expert and spectrum data for pseudodynamic to train the model. So this is an example. We can see here the binning for acetate. So it's worked well. So the main part. After the pre-processing data, we want to train a model. And the idea of the model, of the machine learning model, is connected spectral data to already estimate concentration by the expert in the dynamical pseudo-dynamic data. So how it works, we take the pre-processing data, the pseudo-dynamic data, and we use a model called lasso regression. The goal of this model is automatically choose which bin is important to infer the time series, and also convert this time series in absolute concentration. Once we have that, we can use that to predict automatically the time series concentration in absolute concentration for dynamical data. So about the result of this model, of course, we do cross-validation and checking all the hyperparameters if they are overfitting or not. So on this graph, we can see we estimate very well the which bins is useful to explain the time series of specific metabolic. But they are a bottleneck. We identify the good bins, but sometimes the bins or the peak are very noisy and the concentration are not sufficient to obtain a very good fit. This is the case for certain metabolites. So this is a bottleneck, but machine learning is not magic, badly. So this is the first part of the results. The second part of the results is for the metabolite we estimate well, we have a very good fit. So this is it's a good sign to predict the concentration for dynamical data. About the application for dynamical data, so we have a pre-trained model. We use this pre-trained model to predict the time series for dynamical data. The idea is we give as input the spectrum, preprocessed spectrum of dynamical data, and we run a prediction and we obtain the time series. This is why we win a lot of time, and also we obtain absolute concentration for dynamical data. So this is an example of the results. So for the replicate 5, so the 5 parents, at the top we can see the variation of pH, and under you can see the time series for dynamical data generation. So it's worked very well for the this kind of metabolite, 11 metabolites. And we manage very well the pH variation. Especially, we can see directly on the curve, we keep this kind of variation about the time series on the metabolite. For example, here we switch the pH, we go down the pH, and we obtain the consequences on the metabolite time series. So, in conclusion, this method is robust. It accelerates the trainment of the dynamical data. We obtain absolute concentration to feed our digital twin. In perspective, there are many perspectives in experiment side or in data analysis side. So the first perspective is, for example, the scalability. We can apply this kind of model on broader experiments. For example, broader training set, but also broader experimental data. We can accelerate the pipeline, for example, to connect directly the instrument to the Constellab platform to directly manage the transfer of data. We can also update the algorithm using a more general machine learning algorithm, for example, convolution neural network. Why is this possible? Because we have bioprocess data, so we have a pH variation, so we can use it to better estimation, for example, as a covariate. And finally, as I can see before, it's still a pipeline for data analyst, but the idea is transfer that to a dashboard for the end-to-end user, for example, for experimentalist people. So at Gencovery, we are always aware to a new collaboration. So don't hesitate to contact us if you have some project to manage data or to run analysis pipeline. So don't hesitate. We can just connect to the platform, and there are free access. So if you want to try, don't hesitate. Thank you for the presentation.
Thank you, Thibault. Yes, you can hear me. Huh? Okay, many thanks. I don't see question. Yes, there is Marine who asked a question. Seems like a robust tool, but about the scalability, can you say more about apply that to numerous metabolites? Will it be complicated or very long?
In fact, it's a very good question. This is the idea of the next step. Yes, it's completely possible. The idea is of this kind of pipeline is use already pre-treated data from an expert. So we need this kind of data. So if you want to analyze more metabolite, we need to also analyze this kind of data by an expert to use this kind of data in the pipeline. So it's strongly linked with pseudodynamic data. So yes, it's possible, but like all machine learning model, we need training data with good quality.
Yes, and well, maybe the question is how long it can be and how many. Maybe I had a question about that. So how many training sets you need to train your algorithm?
Not a lot, in fact, due to the model I use, lasso regression. So it's not a neural network model or a more general model. So a small data set, it's enough to learn the parameter, useful parameter. So of course, more data is better, but not a small data set, like for example, 3 or 4 experiments in pseudodynamic data is sufficient. This is also a good point of this kind of pipeline.
Okay, I don't see other question for the moment. Maybe I will ask one. So about the sensitivity, maybe it's quite common question when you do NMR. I was wondering how far you can go to lower concentration of metabolites because you were in the millimolar. Do you see any clue or possibilities in the new development of NMR to go further in terms of sensitivity or concentration?
Yeah. Yes, there are two sides. Because we do sample directly from the bioreactor, so there are no filtration. So of course we lose sensibility with time. This is it's possible to manage it, but in the experimental side. In the data analysis side, we meet this problem. So for example, for a metabolite appear at the end of the experiment, but with a very low concentration. So we can fine-tune the algorithm to obtain a better accuracy, but we have still some limits. So maybe also is linked to training dataset. We train dataset on a very strong peak, strong metabolite. So if you have dataset with bad quality, it's always the case in machine learning. Generally, we train machine learning on high quality data, but we need bad quality data to inform the model. So my point of view is the both side is possible, and we need to do the both side, experimental side and data analysis side.
Okay. So there is another maybe clarification or question from Marine. It's about using different datasets for one sample or one metabolite, like 1D proton, carbon-13, different 2D, etc. And if would the Concept Lab take that in consideration and the different correlation between the signals?
So it's always the same. It's a 1H NMR data. We can say that. Yeah. For the both sides. So for pseudodynamic and dynamical data.
So you do not use different kind of NMR data like the 2D or the carbon-13?
So we don't have this kind of problem.
Okay, I don't see more question. So maybe I can thank you first again, Thibault, of course, for your presentation and for the answers. I would also like to thank all the presenters of today. So the keynote with Tomas Pluskal, so Madina, Niek, and so you, Thibault. Thanks a lot. I think I would like also to thank all the people who attend today the webinar. I think that you can still contact all the presenters if you have questions or if you want to test some different tools that they develop, of course. And I will leave maybe the mic to Marine if you want to say one word at the end or...
Well, no more word than except what you already said. Thank you to the speakers and thank you to the audience. And you will find the recording of the webinar on the RFMF website in a few days. And stay tuned for the next one that will be held on the 9th of October on Fluxomics.
Yes.
Great.
Thank you, everyone.
Thank you very much.